One of the most iconic examples proposed for evolutionary time is the Grand Canyon. Many skeptics of the flood point out that since there is no single layer found in the strata of the canyon that matches their idea of what the Genesis account says happened, that there is simply no geological evidence of Noah's flood, and therefore the flood must be a myth. Many believe and teach that the canyon was carved during the flood. If the canyon was carved during the flood, then why are there not many similar Grand Canyons all over the earth? As we'll see, the evidence within the canyon itself and in the surrounding topography points to a series of unique events that produced this truly Grand Canyon a few centuries after the Genesis flood. To be sure, the canyon, the strata, and the Colorado Plateau on which they rest can all be linked to the flood. However, only hydroplate theory explains and links all these events and features together using physics-based explanation of observed features and simple cause-to-effect reasoning. Any theory of the canyon's formation must first explain the formation of the exposed layers, what caused some to tip at an angle, and what forces or mechanisms caused tipped layers to become beveled cleanly along a nearly horizontal plane. Let's discuss what the layers represent. Do they simply represent vast time according to uniformitarian principles of superposition? Or do they represent other physics-based phenomena? Visitors to the canyon are shown the names of dominant layers of strata. Park geologists believe the sedimentary layers were deposited gradually over nearly 1 billion years, and have assigned geologic periods of time to each of the layer groups. Curiously, amidst the stack of horizontal layers in the canyon, a huge period of alleged time is missing from their own timeline of the past. To the right is a portion of a chart of evolutionary time, produced by the International Commission on Stratigraphy. The intermittent Temple Butte limestone layer is said to have been deposited around 380 million years ago, during the Upper Devonian period. However, the mauve limestone below it is supposed to have been fully deposited 485 million years ago as the Cambrian period ended. It is puzzling that around 100 million years of time is missing from the canyon's layers, with little detail offered as to how the Ordovician, Silurian, and most of the Devonian sediments disappeared so cleanly, where they went, or why they never developed in this region. 100 million years is quite a long time for exposed layers of porous limestone to remain undisturbed, especially when considering that the latest theory of the canyon's formation is that weather and a river cut through all these layers in just 6 million years. Similar problems arise when we consider the certain effect of erosion on all layer boundaries. One of the most striking features of the canyon are the vast, thick, horizontal layers that appear to be neatly stacked like pancakes. Most accept the idea of superposition, that these layers represent hundreds of millions of years of sequential deposit of sediments that hardened into rock. However, if deposited over millions of years as claimed, then erosion between and within layers, cross-contamination, and variation in thickness and purity should all be readily observed, yet any view from the rim indicates otherwise. A good critical question to consider is how did these layers avoid all forms of erosion by the seas which are claimed to have deposited these layers? After each miraculously gentle sea dried up, we are then required to accept that the exposed top layers avoided all forms of wind and water erosion for eons of time, only to be cleanly swept over by yet another equally gentle sea. Apparently each sea carried uniquely pure yet very different sediments for millions of years at a time. We have to swallow this just-so scenario over and over again for each pure, nearly horizontal layer of uniform thickness and differing material composition that we observe. Our present observation of the effect of wind, rain, and temperature cycles on all of today's currently exposed land features demands a much different outcome in the proposed geologic timescale of millions of years. Deposited layers absolutely would experience all forms of erosion, from wave action, tidal effects, exposure to all forms of weather, flooding, seasonal thermal cycles, as well as daily temperature effects. All of these relentless processes would have been continuously working on the flat planar surfaces of each layer for eons. Unlike crystalline rocks such as granite, remember that we are talking about primarily loose sediments and porous sediment rocks, which are particularly vulnerable to erosion. So clearly something more like this is what we should see in between the layers of the canyon. Yet observation shows vast, nearly horizontal, pure layers of fairly uniform thickness neatly stacked. Time is a variable, not a mechanism. Liquefaction of sediments during the flood resulted in particles sorting according to size, shape, and density, which resulted in the rapid formation of thick and pure layers. The vastness and depth of these layers are a testament to the immensity of the forces at play during the flood. The geological principle of superposition assumes the simplified logic that layers are formed individually over time, one on top of the other. Therefore, deep layers are older than shallow layers. We intuitively know layers don't naturally develop between or under layers that are already deposited, so superposition sounds pretty straightforward, and not being presented with any alternatives, it is easy to become convinced that this must be in fact a law of science, as stable as gravitation. Layers of strata must represent time, right? Many are not aware of a very real mechanism caused by gravitation acting on particles in a fluid or fluid-like state. The mechanism is liquefaction. Liquefaction of a soil will produce many layers, all at the same time. In fact, you can see liquefaction for yourself by experiment. Get a couple of 2-liter plastic bottles and fix them to a teeter-totter. Fill one bottle halfway with any combination of mixed soil you wish, and connect a hose between the bottles. Then add water to the other bottle, and very slowly tip the bottles back and forth. Just a few cycles of liquefaction will produce layers all at once. So while superposition is a principle that can be useful if applied carefully, it does make assumptions that can lead to completely incorrect conclusions. Those who study the hydroplate theory know the conditions that caused liquefaction as sediments were deposited during the flood. Explanation of these conditions and detailed explanation of the physics governing liquefaction are covered in the hydroplate theory overview series of videos. While several mechanisms caused liquefaction of sediments during the flood, one of the mechanisms known as the compression event produced not only liquefaction but also caused several other features to form in the canyon. While these features require a great deal of imagination about the power of time for uniformitarian theories, we'll see that all features have a firm, physics-based explanation which serve as strong evidence for hydroplate theory's compression event. Evidences of the compression event that are easiest to see are the canyon's unconformities between layers and the intrusion of quartz into crushed granite. You probably noticed the tipped layers below the tapete sandstone in this graphic. The bevel line of contact between these tipped layers and the horizontal layers above is called the Great Unconformity. The Great Unconformity is alleged to represent around 1/2 billion years of time, where a mountain's tipped layers were horizontally beveled off by an undefined process. Again, time is a variable, not a mechanism. Whether the Great Unconformity represents 1/2 billion years or not, no mechanism is provided that explains this horizontal beveling of tipped layers. Vague reference to erosion over time does not suffice to explain this feature. Erosion over such a long time should have left a substantial pattern of deep erosion, not a beveled, nearly horizontal plane. So what mechanism could produce this beveled feature? Another question to ask is what tipped the layers under the unconformity in the first place? Beveling tipped layers horizontally requires relative motion against something from above. Tipping layers requires force on a massive scale such that continental rock below them is compressed, buckles up, and tips the layers. What mechanism or series of mechanisms could cause all of this to happen? Hydroplate theory explains that midway through the flood, Earth's continents slid rapidly on water. This sliding of continental plates is at the root of the theory's name, hydroplate. We will not take time here to cover the forces and mechanisms leading to the rapid sliding. However, this material is covered in detail by the hydroplate theory overview series of presentations. What we will cover here is the evidence produced as a result of this rapid sliding of plates on water. As the Atlantic mid-oceanic ridge rose up, continental plates slid away, the African and Eurasian continental plates slid to the east, while the American plates slid to the west, on a nearly frictionless layer of supercritical water. As the leading edge of the plates crashed into the mantle and began skidding to a stop, the granite buckled and crumpled, Earth's major mountain chains like the Andes and the Rockies were formed in hours. The compression event explains why both of these major chains are located on the western edges of the American continents. Uncemented sediments laid down during the flood and sorted by liquefaction into layers were tilted and tipped as the continent thickened and rose up. Beneath the sediments, the granite material experienced even more extreme compression, fracture, heating, and melting. The spiderweb of fractures in the granite soon filled with molten quartz. Why quartz? Of all the materials that make up granite, quartz melts at the lowest temperature. So as heat from compression and shearing of the granite increased, quartz always melted and flowed first. Therefore, veins in the fractures and along the shear lines were filled with quartz. This evidence is entirely consistent with the westward direction the American hydroplate slid away from the mid-Atlantic ridge. Those who have not considered the physical mechanisms supporting rapid continental drift that ended in the compression event explain the flat Cambrian-Precambrian interface as the result of hundreds of millions of years of erosion. For them, unimaginable time tends to explain everything. In contrast, we see hydroplate theory offers a physics-based reasoning. The granite walls of several deep canyons in North America offer much evidence of this extreme compression, sliding, and relative movement within the continental rock. Here we see Colorado's Gunnison Canyon. These areas indeed show that the material has been rapidly crushed and powerfully injected with a spider web of quartz veins. Only the heat generated by rapid crushing would explain how molten quartz could be injected throughout such a large volume of colder, solid rock. If this material were injected slowly over millions of years, the quartz would have cooled, solidified quickly, and not traveled so completely through even the thinnest of fractures. Any who work in the casting or injection molding industries can attest to the tremendous challenge of getting molten material to flow through both thick and thin mold walls. The thinner the vein, the greater the challenge. Any theory must take a hard look at the thinnest of these veins, where heat transfer to the walls of the vein would be tremendous, and explain how such a thin flow of hot material could flow without freezing against the colder, solid walls. Here, gradual processes and the variable of great time will not overcome the stark demands of thermodynamics and heat transfer that we see embedded in the rock. This material had to have been heated and crushed rapidly, and the quartz within had to be melted and injected just as rapidly under tremendous pressure. Guess what? In the Grand Canyon, under all the sedimentary layers, this same spiderweb of quartz-filled cracks in crystalline rock is found deep in the walls of the canyon's inner gorge. This basement rock in the canyon is referred to as the Vishnu Schist. While the granite continent was sliding, melting, crushing, and buckling its way to a stop, the sediments piled on what eventually became the Colorado Plateau felt the same sudden force of deceleration. While the basement rocks show that the material was rapidly crushed, many sedimentary layers further show that this crushing and compression must have been due to a rapid and massive deceleration and sliding event. How else was this sandstone beveled so evenly? This again points to a rapid one-time sliding event, where tipped layers sheared along a horizontal plane and were beveled by sediments above. Similar evidence in the sediments is seen on a large scale. The Grand Canyon's Great Unconformity and other unconformities, such as the one pictured here, looking north from the canyon's Desert View Watchtower, reveal the large-scale extent of beveling. Layers below appear to have been cleanly sheared off, with flat layers then stacked above. A less noticeable feature in the canyon walls presents yet more extremely strong evidence of hydroplate theory's compression event. Buried deep in the layers of the canyon, at the base of the much photographed formation referred to as Isis Temple, is a partially exposed and extremely important rock. This rarely spoken of evidence shows that the layers surrounding the rock had to all have been uncemented at the same time that they were deposited. It also shows that the unhardened layers were rapidly moving in a massive westward flow, as hydroplate theory would expect, before they came to a rest at their current position. This angular block, weighing an estimated 5 to 10 tons, casts great doubt on gradual layers and sequential hardening of deposits over eons of time. At these coordinates, The block of quartzite, which has obviously come from the thick quartzite layer below, is clearly visible in the canyon wall. Ask yourself, what scenario of events could lift this rock so cleanly to its current position? Hardened rock layers would never smoothly deform around and encase the rock. Surrounding layers above and below the sharp features of the block have clearly deformed around the edges. Only soft, water-laden sediments would deform locally like this. The block's shape retains sharp sides throughout its thickness. There is no evidence of weathering that would be expected if this block was partially exposed to weather for eons and gradually buried. Geology professor Arthur V. Chadwick correctly identified the lifting force. A very dense, rapidly flowing sand, mud, and water slurry which plucked the block off the tipped Precambrian lower quartzite layers far upstream of the flow. The easiest way to lift and transport such a heavy block is in a dense, liquefied, and therefore very buoyant sediment and water mixture that is flowing at high velocity. Unlike any other theory, hydroplate theory precisely explains this rock's unique position. In fact, as we'll see, every aspect of this, even the orientation of the rock within the layers, precisely matches hydroplate theory's expectations. This rapid transport occurred immediately above the Cambrian-Precambrian interface during hydroplate theory's compression event. Remember, this interface is what has been termed the Great Unconformity by those holding to uniformitarian geology. But as you've seen in the hydroplate theory overview, there is a simple physics-based explanation once the prevailing dogmas of evolution are abandoned. The Great Unconformity is actually the natural shear line resulting from the rapid deceleration, sliding, and beveling of sediment layers. Rather than representing 1/2 billion years of time and mysterious erosion processes, the Great Unconformity formed in hours due to deceleration and sliding on a continental scale. Note the camera here is looking north, therefore the slurry slid from east to west. The crushing, compression, and deceleration of the compression event readily explains the horizontal sliding of soft layers seen in the canyon walls, as well as the spiderweb intrusion of quartz throughout the crushed granitic material. If you'd have placed an indicator in the soft sediment layers produced by the flood before the compression event, it would have moved with the rapidly sliding plates and sediments. But as the plates crashed and began slowing, the indicator would have bent in the direction of the deceleration, just as your head bends forward when you slam on the brakes in a car. As this deceleration occurred, resistances slowed the plate, compressing it, causing it to buckle up and deform at points of weakness. This caused unhardened layers still saturated with water to incline and deform with the buckling plate surface. As decelerating layers were lifted up above the apex of buckled regions, uncemented particles above were no longer supported by the solid crystalline rock below, and a shear plane quickly developed between supported and unsupported grains. Below the sliding slurry, a sand layer decelerated and compressed first. That rapid compression squeezed up water which lubricated the slide above and aided lubrication of the layers above, and heated the quartz sand. This heat and compression changed the sand layer into a metamorphic rock called quartzite. Eventually, the unsupported sediments slid westward along the shear plane, which easily beveled the layers below and caused further liquefaction and horizontal layering of the sediments above. As this occurred, a block from the quartzite below broke away and was lifted and carried west by the flowing sediments. As the flow slowed, the heavy block gently settled and locally deformed the soft layers it was encased in. Centuries later, this rock was exposed as the Grand Canyon was carved, revealing strong evidence of catastrophic flowing of soft sediments while generating many difficult questions for those who believed that the canyon's layers were deposited and hardened slowly. There's probably a reason you don't see this rock pictured at the Grand Canyon's Visitor Center. It certainly doesn't fit popular narrative. However, all of these features in the canyon's layers align with hydroplate theory's compression event of rapid sliding, compression, buckling, beveling, and liquefaction occurring on a continental scale in an east to west direction. These mechanisms produced the layers and their unique features. Next, we'll discuss and critique the popular idea that the Colorado River cut the Grand Canyon. The canyon exposes another striking feature that is important to observe with a careful eye. In the middle of the canyon, beneath all the sedimentary layers, is a 46-mile-long deep inner gorge, where the crushed basement crystalline rock layer of the Vishnu schist is exposed. The rock walls of the inner gorge are jagged and very steep. The gorge's depth extends into this crystalline rock layer up to 1,200 feet at its deepest point, making it the deepest part of the canyon. We are dogmatically taught that the mighty Colorado River carved the Grand Canyon, including this deep inner gorge. Take note of how the inner gorge aligns with the raised elevation of the green forested Kaibab Plateau. The reason for this alignment will become clear as we discover the true cause behind the formation of the inner gorge. As we'll see, the river, which is pretty tame compared to other rivers around the world, could never have cut these features no matter how much time is allowed. Let's look at the river cutting claim more carefully. Sure, the river is removing sediments, but an important question to consider is whether the river is actually cutting into and deepening the inner gorge. Hydroplate theory observes that the river is not cutting into the gorge. It cannot, because the river's bottom is covered with around 75 feet of sediments and huge boulders which are not moving. The sediments and boulders in contact with the gorge's steep sidewalls actually protect the hard crystalline rock face from being cut by the flowing river. We can see this more clearly by viewing a section view of the flowing river in the canyon's inner gorge. From the side now, we can evaluate the conditions occurring in the canyon as the river flows over these sediments. The river's flow certainly stirs up and carries the first few inches of sediment out of the canyon. However, below this boundary a line forms, where the energy from the flowing river is not transmitted to the deeper sediment. Fluid dynamics can help us see why this is. The river flows fastest on the surface in the middle of the river where drag is minimal. Progressing deeper into the flow, velocity progressively decreases as resistance with the sides and the floor increase. The depth of this boundary line will vary with the speed of the flowing river. However, even before the Glen Canyon Dam existed, the output of the Colorado River, even during flash flooding, would never have been able to penetrate deep enough into the boulders and sediment to make them move and cut against the rock walls. If the sediments against the inner gorge cannot move or flow, then there is no mechanism for cutting deeper into the canyon's rock. Another problem with the idea that the river cut the canyon is that we observe extensive side canyons which are almost as deep as the Grand Canyon itself. If the Colorado River's near constant flow cut down to this current level over millions of years, what water source is supposed to have cut these huge riverless side canyons to nearly the same depth? This canyon along the Bright Angel Fault stretches over 11 miles horizontally away from the Colorado River. This major issue is never addressed adequately. Soon we'll see how unique conditions in the sediments themselves after the flood produced these side canyons. So what forces cut these side canyons? The hydroplate theory will provide a simple and reasonable answer. Another trait of the inner gorge is that it is so deep and steep, with jagged sidewalls. If the river truly cut this major feature of the canyon, we should ask if these observations line up with the proposed mechanism. Why didn't the river cut sideways into softer sediments once it encountered the hard crystalline rock? Why are the sides still jagged after millions of years of river flow? This scaled cross-section of the canyon shows how deep and steep the inner gorge is compared to its surroundings. The black layer represents the crystalline rock that has been penetrated, forming the inner gorge. At this scale, the insignificance of the Colorado's flow can be seen, as it would be smaller than the very tip of the white arrow that is pointing at the bottom of the gorge. This view reveals the very jagged, fractured nature of the inner gorge, which again extends up to 1,200 feet into the hard crystalline rock layer. Flowing water smooths and rounds off jagged features protruding into its flow. If the river cut the inner gorge, the jagged sides should have also been smoothed out over millions of years. A river cutting the canyon would not be expected to produce the steep, deep inner gorge in hard crystalline rock. As the river eroded through the softer sedimentary layers and reached the surface of the hard granitic rock, we should pause and ask which is more likely. Would the river cut sideways into the softer porous material of the sediments, or down into the dense interlocked crystalline rock? Of course, the path of least resistance would be exploited as we'd expect. The side walls of the canyon would continue to erode at a rapid pace, while the harder rock below would see comparatively little erosion. Notice here that the cross-sectional shape of the river would change as the sides eroded. Unless significant increases of water from unknown sources are identified, the river width would increase as depth decreased. Both of these changes would slow the river's flow speed, decreasing its ability to continue to erode sideways, much less cut down into harder material. Yet by passively accepting that the river cut the canyon, we must accept that the opposite of all expectations occurred, and the river sliced right into the harder rock. Let's take a moment to clarify the point I'm making. There are many examples where water carrying even little sediment has rounded off and noticeably smooth surfaces of hard granitic rock in many mountain streams. Yet the very gritty, quote, mighty Colorado River has clearly done very little work on the walls of the inner gorge. The photos to the right are all from Google Earth, using the Street View tool along the Colorado River in the inner gorge. Take a virtual tour yourself in Google Earth, and as you do, ask yourself if the river could cut over 1,000 feet down into these crystalline rock walls, without smoothing surfaces and edges, as so many other less gritty streams have. Could a completely different mechanism have formed the inner gorge recently, leaving rough, still jagged surfaces today? I believe the answer is yes, and by the end of this presentation we'll see why these walls of the inner gorge are so steep and jagged. For now, let's set aside the still jagged walls and continue to explore any possibility that the river could cut the gorge. If a fault were to be found that parallels the Colorado River, then we might have a case for why the river cut into the rock. However, no fault coinciding with the inner gorge has ever been reported. Many faults are found in the canyon. Surprisingly, though, they generally run perpendicular to the river's flow. We then must ask why the river did not follow any of these easier paths along faults. Here we can see a map of the region's faults relative to the river. In spite of many opportunities, the river has ignored all of these deep faults. Here is a clear close-up picture of 19 Mile Fault looking in the direction of the arrow. Looking southeast across Marble Canyon, we see this perpendicular fault's displacement of sedimentary layers and the effect on the surface for many miles beyond the canyon. Another challenge to the idea that the river cut the canyon is the Kaibab Plateau. How could the river have cut uphill through this feature, which is several thousand feet above the river? The Kaibab, highlighted here, is an upwarp in the topography on the much larger Colorado Plateau. As we'll see, the Kaibab upwarp, often referred to as a plateau, greatly displaced the canyon's layers. The Kaibab upwarp has lifted the layers up in this area a few thousand feet relative to the surroundings. If the Kaibab existed before the river, then the river traveling southwest would have been stopped by the upwarp and either reversed its flow or have cut a much different path, one of the least resistance around the upwarp. Against all expectations, however, the river turns almost 90 degrees uphill and diagonally through the upwarped topography. If we started at point A and cut through the layers of the plateau and canyon to point B, and viewed them from the side along this line, we would see this. Here we see the problem more clearly. Below is the 100-mile section of topography along our white line between points A and B. In the view, the river flows from right to left, yet the topography is uphill. Starting on the rim of the Kaibab limestone above Marble Canyon, we move out from between Vermilion and Echo Cliffs toward the upwarp. Notice that everything arches up toward the Grand Canyon. Drop into a side canyon, then up a steep monocline onto the Kaibab Plateau. Drop down into the Grand Canyon, then up onto the south rim, and descend off of the south face of the Kaibab Plateau. So the obvious question is, how does a river cut uphill through thousands of feet of hardened rock? Cutting from here to here. Some propose that the Colorado must have cut at precise just so rates through the rock of the Kaibab as it rose up thousands of feet for millions of years. This is a fantastically optimistic idea, and another implausible just so story. Of course, the forces and mechanisms that produce this carefully balanced just so story are rarely addressed in any specific detail that can be scrutinized. We again see that the river, even with lots of time, is very lacking and fails to explain the complexity of what we observe. Overlaying the detail of the disturbed layers reveals even more evidence of how the plateau has lifted relative to its surroundings. Here we see what is called a monocline, where layers have been distorted and displaced relative to each other as material rose to the west of the monocline. Hydroplate theory will reveal the mechanisms that cause these features as well as the dramatic arching in the layers. This is called the East Kaibab monocline. To the right of the monocline, the layers are thinned, compressed, and arched up as you head left toward the Grand Canyon. Any theory of how the canyon formed must also address in detail how this dominant feature formed. That is, the Kaibab Plateau, which rises up from the Colorado Plateau. Any theory of the Grand Canyon must offer a mechanism of how the Colorado Plateau formed as well. See Part 4 of the Overview series of presentations to learn how hydroplate theory answers the double-ended mystery of how the Colorado Plateau rose up while depressing the Mohorovicic discontinuity down into the mantle at the same time. Only hydroplate theory offers a defined mechanism for producing plateaus. To understand how the canyon did form, we need to be familiar with many other features outside the canyon itself. For most visitors, the tiny Colorado River is at least visible in spots from the rim, and all the popular theories claim that the river was the cause, and therefore most passively accept this extremely simplistic explanation of the canyon's formation. However, most of us who visit the canyon's edge see only a fraction of the canyon, which is of course very large. But these external features are so large and spread out that they are almost impossible to see from the rim of the canyon or even a plane or a helicopter. Because they are not seen, few realize these surrounding features' significance to the canyon's actual formation. For example, few realize that when they stand on the rim looking into the canyon, that they are actually standing in the bottom of a much larger hole. Over 1,000 feet of what geologists refer to as Mesozoic sediments are missing from both rims of the canyon and for hundreds of square miles in all directions. To the north of the canyon we see the remnants of these missing layers, in the formations of Echo and Vermilion cliffs, which rise around 2,000 feet above the Kaibab limestone, which forms the top rim of the canyon. Here is a photo I took from the highway that runs along the top of the Kaibab limestone at the front base of Echo Cliffs. Far in the distance you can see the corresponding Vermilion cliff system. Further down the highway and up into the funnel-shaped region between these two cliffs, looking back, we can see that the layers are arched up toward the Grand Canyon to the south. What caused all these layers to arch up in this direction? Also, some places further to the south, like Red Butte, show remnants of these same layer sequences. Red Butte rises 1,000 feet above the Kaibab limestone and is capped with a thick layer of volcanic material. The same Part 4 in the Hydroplate Overview series reveals how this non-volcanic butte became capped with volcanic rock. For now, we want to know where all this missing material went and how it was removed. So much Mesozoic material has been removed over 10,000 square miles around the canyon area that it has been termed the Great Denudation. At this point, we see several observations that show the inadequacy of the Colorado River cutting the canyon itself, the inner gorge, and its many side canyons. We've discovered the tremendous challenge of explaining how the river could have cut through the mountainously high Kaibab Plateau, and have begun to see many details in the arched layers that raise more unanswered questions about their formation. Even more puzzling, we realize a larger problem than the canyon itself is explaining the missing upper layers of the Great Denudation. There is a reasonable explanation for all of this, but first we need to learn about what caused the Colorado Plateau to rise in the first place, and the evidence of the unique initial conditions on top of the plateau, which explain the odd geology that is found all across the top of this single plateau, which is unique to any other plateau on Earth. While the canyon is estimated to have eroded 800 cubic miles of material, these missing Mesozoic layers that have been scoured off the top of the canyon and all of its surroundings represent approximately 2,000 cubic miles of removed material. So before a theory can even begin to discuss how the canyon was excavated, it first must resolve how the 2,000 cubic miles of Mesozoic sediments were first removed over this vast 10,000 square mile area. There is much evidence of two tremendous ancient lake beds that lie to the east of the canyon, Hopi Lake to the south and the much larger Grand Lake discovered by Walt Brown to the north. The approximate volume of Grand Lake was nearly double the size of Lake Michigan. Hopi Lake's volume was nearly that of Lake Huron. Recognizing the existence of these lakes is critical to resolving how so much sediment was removed in and around the Grand Canyon. For just a taste of the size of Grand Lake, here is a view of Monument Valley located here, looking south in the direction of the arrow, and seeing little more than what is inside the red circle. The shoreline of Grand Lake would have been at the base of those cliffs in the distance. As you can see here, in this basin, there are many unique scoured and eroded formations both in and around these gigantic lake beds. Obviously, the mesa's layers pictured here were once all connected. What mechanism removed all this material, and where did it go? Why didn't these mesas get eroded as well? Very unique conditions are required to produce these features. These huge, ancient post-flood lakes, and the manner in which they drained played a major role in producing these features, which make the desert Southwest landscape so picturesque and unique. Some cast doubt that these ancient lakes ever existed on the plateau, citing that there are not consistent nor distinct enough shorelines as expected from a large body of water. This is a fair critique. Lakes generally leave shoreline evidence. This critique, of course, assumes several steady-state conditions around and below the lake. So why don't these lake beds have shorelines? In a bit, we'll see several unique mechanisms were occurring on the plateau as it developed, which explain why these lakes' shorelines did not survive. First, here is a true color photo of the Colorado Plateau and its surroundings produced by NASA. Right away, it is plain to see that a distinct area of discoloration exists on the plateau to the north and east of the Grand Canyon. Closer inspection of this discoloration begins to reveal that this area, in contrast to its surroundings, has been somewhat uniformly scoured by water. This area is a globally unique region, with a concentration of features and formations unlike anywhere else on Earth. If the Grand Canyon and surrounding areas were simply the result of water runoff after the flood, then why do we not see the same features, formations, and scouring in similar concentration on every continent? The same can be asked of those who propose that these formations are simply the result of chance, time, wind, and weather. Why are so many features so concentrated on the plateau in this etched region? Looking at this same area with the proposed lakes superimposed, let's cover some of the more spectacular formations and take note of each's proximity to the lakes. Here is Arches National Park, which reveals that both hard and soft regions of sediment still existed throughout multiple layers. The layers of rock we see today had not uniformly hardened at the time of this erosion. Canyonlands National Park, which overlooks a vast, dry basin whose floor itself has had deeper irregular canyons eroded into it. This extreme and deep erosion of a lake floor only happens if a large amount of water drains very quickly, such that subsurface flow and drainage can sweep the sediments out of the basin. These features in the basin are strong evidence of rapid drainage of a large volume of deep water. Bryce Canyon and Zion Canyon both eroded by subsurface flow of top layers on the perimeter of the plain of the Great Denudation. San Juan River, which along with many other rivers in these basins, severely goosenecks back and forth, again an indicator of much subsurface flow. Monument Valley, where a great deal of sediment has vanished, leaving many flat-topped mesas. This erosion and clean sweeping of sediments again points to rapid discharge and drainage of deep water. Rock Point, Arizona, where multiple large erosion pits up to 20 stories deep are found in an area where there is no source of water to carve them. Canyon de Chelly, where 5 side canyons converge on an 800-foot spire. Yet again, today there is no water source to explain this strange erosion. Coal Mine Mesa, an area in Hopi Lake's basin rich with petrified wood and a thin layer of coal, where hundreds of square miles of the basin have been eroded by what appears to be a great deal of subsurface flow, similar to the irregular erosion seen in Canyonlands National Park in Grand Lakes Basin. Painted Desert is found in Hopi Lake's basin. This southern end of Hopi Lake is also the location of Arizona's Petrified National Forest. Initially warm, silica-rich post-flood lakes would naturally hold some of the floating remnants of pre-flood forests. As the lakes cooled over time, the silica came out of solution and hardened in the saturated fibers of the trees, causing petrification. Watch the Hydroplate Theory overview series of presentations to see why the post-flood waters were warm and how they ended up containing so many dissolved minerals. Finally, this region has the greatest concentration of slot canyons in the world. Again, notice how most of these locations are situated within the proposed lakebed regions. These fantastically unique formations all speak to having been formed by a large volume of flowing water over and through many layers of sediment that had not fully hardened into rock. Hydroplate theory proposes that these scoured basins and their many strange yet beautiful formations were formed as these two ancient lakes quickly discharged their volume in a matter of weeks. This presentation will show precisely how this happened. Another key point to understand is that in addition to the water content of these lakes, the sediments beneath and surrounding them were still not fully hardened into solid rock, and were still permeated with water left over from the flood. This water, still trapped in the sediments, played a major role in defining the unique landscape on the Colorado Plateau that we see today. Notice how many of the locations, which are not in the lake basins, are erosional areas near the shoreline. Remember, this is a dry desert region where there are few sources of water to carve these features. And hardened rock would never have eroded in the manner we see. Time and again we will see strong evidence that many of these layers we see in this area had to have been mostly soft in places and still contained much water between their uncemented particles. For several centuries after the flood, as the Rocky Mountains sank, the Colorado Plateau was hydraulically lifted. Friction from the sinking Rocky Mountains produced large volumes of magma, which was then injected between the former roof and floor of the collapsed subterranean water chamber, the easiest path of escape. Two huge inland lakes, Grand and Hopi Lake, were located on this forming plateau and were also lifted. It is this wholly unique scenario of a plateau lifting lakes a mile high without them spilling that created the completely unique topography of the southwestern U.S. Many plateaus have formed, and many ancient lake basins have formed and slowly drained or dried up all around the earth. But only here, in the Four Corners area, did a plateau lift two lakes so high above their surroundings and leave so much evidence of catastrophic breach and draining. Here is a better view of Hydroplate theory's proposed hydraulic lifting mechanism. Over the centuries following this event, the magma under the tremendous weight of the mountains was slowly injected under adjacent thinner sections of continental rock. Notice the lack of mystery here. Rather than vague terms like uplift, rifting, and crustal stresses, Hydroplate theory is very specific about the forces. This all happened as a natural function of gravity acting on massive mountains as they slowly sank like giant pistons. The fluid beneath was injected sideways under the thinner adjacent crust until enough pressure was generated to shear the material. These shear lines formed somewhat vertical faults in the continent. Once blocks were either restrained or rose high enough, continued pressure lifted adjacent material, which also sheared. In this way, the Colorado Plateau was block faulted and raised a block at a time by hydraulic lifting. We see the stair-step outlines of some of these blocks today. The Book Cliffs, the Roan Cliffs, and the Grand Staircase consisting of the pink, gray, white, chocolate, and vermilion cliff systems all formed in this way. As the Colorado Plateau was lifted by the uneven lifting of these blocks, so too were the post-flood lakes. This is one of the conditions that explain why these lakes' shorelines, especially Grand Lake's wide and spread out shoreline, are not well defined. As various blocks lifted over time at different points, the shape and location of the shore was constantly shifting, so no clear shoreline was ever eroded in one spot. For Grand Lake, the Vermilion Cliff System formed its southern boundary, acting like a natural dam. As years passed, these post-flood lakes grew as precipitation and drainage collected in these natural basins. The ever-increasing water level was another factor that prevented clear shorelines from developing around the lakes. As the plateaus rose, the potential energy of these huge volumes of water increased. Remember, Grand Lake alone grew to an estimated volume nearly double that of Lake Michigan. The difference being that Grand Lake's volume was lifted over 1 mile above its surroundings. This unstable and dangerous situation was exacerbated by the fact that many post-flood sedimentary layers forming the lake's floor and shoreline had not yet hardened into rock, and were still permeated with a great deal of water of their own. Grand Lake's water eventually found a path through these soft sediments and exited the Vermilion Cliff System. This set in motion a chain of catastrophic events that would completely reshape the landscape below to the left of this view. The sudden and complete discharge of Grand and later Hopi Lake in just weeks further explains why there is little remaining shoreline left today. As the lake filled its basin, it established a high water table in the surrounding porous sediments, which were not fully cemented. As the lake rapidly drained in weeks, the water in the surrounding shore found itself far above the rapidly dropping water table. Naturally, the water around the perimeter spilled out of the sediments, adding to the original volume of the lake as it drained. In doing so, the resulting erosion of the soft sediments removed much of whatever shoreline remained at the time of the lake's breach. This is why today we see unusual scouring and erosion from apparently large sources of water, both in and around these large yet very dry basins, with little to no shoreline remaining. We see much evidence of subsurface flow as water eroded soft sediment from the surrounding shoreline's higher ground. This explains the unique erosion seen in Canyon de Chelly and many other side canyons that ring the perimeter of the lake bed. Likewise, violent erosion occurred from under the lake floors as high-pressure water erupted up from saturated sediments below. Local areas where sediment had begun to harden, and high points or islands in the lake's topography that placed more weight on the sediments below them survived the mass erosion and remain today as the unique mesas and spires which are so common in this region. This explains how so much water seemingly came up from the ground, ripping up hundreds of square miles of Hopi Lake's floor, and excavated so many deep pits and slot canyons in Grand Lake's basin. Soon we'll see where all the sediment removed from these basins ended up. Removed floor sediment exposed many of the block-faulted shear lines in the sediments. As water and sediment drained, water began to flow and erode sediment along these shear lines. This created many narrow, deep pits and slots in the basin floor, which briefly filled and flowed as even more subsurface water escaped the remaining sediments. Today, these very narrow and very deep canyons are explored and marveled at by those who visit the many slot canyons in and around the now dry lake bed. Some speculate in vain that time, wind, and undefined sources of surface water somehow cut these deep, narrow channels. Here we see the true source was a brief, one-time flow of subsurface water along sediment shear lines as a very large lake catastrophically drained. Now that we've seen hydroplate theory's explanation of the initial conditions that existed under the hydraulically lifted Colorado Plateau, and the evidence of unique conditions above it, we can now discuss the chain of events that carved the canyon and resulted in the many strange features in the surrounding topography. The key evidence to unlocking what happened starts with this formation on the plateau. Rarely noticed or discussed, it links the ancient lake region to the Grand Canyon. This large, peculiar, funnel-shaped feature is found in the remaining Mesozoic layers of Vermilion and Echo cliff faces. Many who visit the area have driven within and around it without notice on their way to more spectacular sights. So let's focus on this huge funnel-shaped feature which links the Grand Canyon to the lake bed region. The widening funnel shape is characteristic of the erosion pattern of a large volume of water escaping through a spillway. The difference being that this erosion pattern is on a massive scale. If a large amount of rapidly flowing water did not cut this feature, then I ask, what did? Certainly not the tiny Colorado River seen here far below in the bottom of Marble Canyon. And why is it funnel-shaped? and opening in the direction pointing directly toward the Grand Canyon. At the wide end, this channel is 12 miles across and 2,000 feet deep. Obviously, before Echo and Vermilion cliffs were carved out, the sediments were continuous between them and bounded the southern shoreline of Grand Lake. Hydroplate theory will show this huge funnel-shaped channel is glaring evidence of a massive catastrophic lake breach. Here is another view looking directly down the mouth of the funnel, with an elevation cross-section view across the mouth of the funnel. It is hard to comprehend the size of this feature, so a comparison will help. About 750,000 gallons of water flow over the falls of Niagara every second. For a sense of scale, here is a view of the American and Canadian falls at Niagara. This view of the falls is approximately 3/4 of a mile across. Now observe how Niagara compares to the mouth of the funnel. Imagine the volume of flow that would have carved out this funnel. The scale of this event is staggering to contemplate. Now, with all this in mind, let's look at the mechanisms involved in producing this peculiar topography that has long perplexed those who choose to believe a river cut the canyon. In this view, we see the familiar funnel shape of Echo and Vermilion cliffs. As seen previously, the white line is the location of the 100-mile wide section below showing the topography. In the background of the profile section view, I've added the raised topography of the Vermilion cliffs, representing the missing Mesozoic layers which originally covered the entire area. As we progress, we'll discuss the actual cause-to-effect mechanisms that scoured off the Mesozoic layers west of the funnel, produced both the general and gradual arching of layers, as well as the extreme arching up of the Kaibab plateau, carving of the Grand Canyon, and of course the formation of the inner gorge of the Grand Canyon, as well as its many side canyons. Any theory of the canyon's origin must at a minimum explain the causal forces and mechanisms which produced each of these striking topographical features. Remember this section view as we will wind back the clock to pre-canyon topography and show the sequential series of events that produced this. Several deep pits atop the edge of Echo Cliffs reveal a rough picture of events that compromised Grand Lake's shore. These pits are actually large potholes. A pothole forms when a rock becomes caught in a spinning eddy current or vortex of flowing water that is whirled around in the mud at one spot. Potholes are generally small and form in fast-flowing streams. As you can see, these potholes are rather large. Consider how odd to find a large deep pothole at the top of a nearly 2,000-foot cliff. Today, this area is at around 6,300 feet above sea level according to Google Earth. Make a mental note that at this location, the Colorado River is over 4¼ miles away and well over 3,300 feet lower in elevation than these potholes. The Colorado River may be described as mighty, but it is not magical. How was so much water at this high altitude flowing powerfully enough to produce large eddy currents capable of spinning large boulders in still soft sediment? This is yet another striking piece of confounding evidence you will not find at the Grand Canyon's Visitors Center. But ignoring evidence does not make it go away, nor any less important. From above, we see this region as it is today, but with Grand Lake superimposed to the north and Hopi Lake to the southeast. Before the breaching of Grand Lake, the southwest end of the Colorado Plateau was a wide, generally flat plain of soft sediments. The topography of the Vermilion Cliff system was not arched up toward the area where the funnel is today. Rather, it was an elevated, generally level berm that bound the southern shore of Grand Lake. At some point, Grand Lake's southern shore began spilling catastrophically over the elevated Vermilion topography. This was possibly due to either the breaching of another lake further to the north that spilled into Grand Lake, or a seismic event from a sudden shift in the Colorado Plateau's block faults, which altered the shoreline level of the lake, causing it to suddenly spill over its southwest shore. Whatever the cause, a large flow of water began swiftly flowing over this area for a time. This explains how the potholes would have formed and be found in such an odd location today. How they ended up at the edge of an arched 2,000-foot cliff will become clear shortly. The soft sediments were also compromised from below as water found a path through the unsolidified material. Once the Vermilion Cliffs were compromised from within, a path quickly eroded the unstable Mesozoic layers, which slumped down, and quickly formed into an 18-mile-long open spillway. Let's now look again at our cross-section along the same white line in this pre-canyon state. Before Grand Lake breached, the weight of the sediments pushing down on the continent was in a balanced state. But this plateau region of the continent had been hydraulically lifted up from below and was still suspended on a slurry of pressurized liquid magma. Here the blue arrows represent the weight of the top layers of sediments. Grand Lake breaches. The waters rushing into the lower plain began to quickly excavate and transport the upper layers to the west. As this happened, the missing weight was no longer there to react the pressure from the magma below, so that portion of the plateau began to rise once more. The result is that the faulted portion of the continent begins to rise. As this happens, the layers above begin to arch up as well. As more and more sediments were washed away, more weight was removed, and the landscape arched further. The mountains, which had stabilized after raising the plateau to its pre-breach state, now felt the drop in hydraulic pressure due to the sudden imbalance. Again, gravity drove the mountains down like a giant piston, hydraulically injecting more magma under the plateau, seeking a new equilibrium. The waters continued to scour away the Mesozoic layers, until a thick layer of limestone which had already hardened into rock was exposed. The Kaibab limestone layer was able to resist erosion better than the other softer layers above. Rather than continuing to erode down, the current continued eroding the soft sides of the spillway, naturally widening it into the funnel shape. The erosion widened the downstream end of the channel to about 12 miles across. This exposed much of the Kaibab limestone, and in the process formed Echo and Vermilion Cliffs. To get a sense of the scale of this, here is a picture taken in the direction of the green arrow from US Highway 89 as it climbs up the side of Echo Cliffs. This picture is taken around halfway up Echo Cliffs, looking across the 12-mile opening toward Vermilion Cliffs. Marble Canyon and one of its side canyons can be seen in the floor of the spillway below. It is hard to comprehend the tremendous volume of water and sediment gushing out of this breach point. Before the funnel was formed, the weight of sediments was evenly distributed. A section would look like this. As the funnel was eroded, the weight of the sediments was removed. Although the exposed Kaibab limestone on the funnel's floor was hard, it was very brittle and resting above still soft sediments which now exerted great pressure below the limestone. This placed the brittle exposed limestone into a bending state. The brittle limestone floor cracked in tension down the middle of the wide channel. As the funnel's floor fractured and rose, the rims of the two newly formed cliffs also were lifted. This explains why the potholes found along Echo Cliffs are found on raised topography at the edge of a cliff. Had the funnel's erosion been just a few feet wider, this important evidence would have been lost. In this way, Marble Canyon began to form as a tension crack. By now we see that time plus erosion times imagination does not equal the Grand Canyon and its many features. Instead, we see that careful examination of the entire area of the Colorado Plateau reveals the evidence which clearly points to the catastrophic mechanism of Grand Lake's breaching. This carved the huge funnel-shaped spillway near Page, Arizona, and split its limestone floor, producing Marble Canyon. Now we will link the remaining mysteries of Grand Canyon's formation in roughly chronological order, continuing to rely on known mechanics, failure analysis, and cause-to-effect reasoning as our guide. This crack in the Kaibab limestone also traveled south, following the paths of weakness where the most erosion of the top sediments had occurred. The energy released during this fracture event likely caused the next catastrophic event, which you may be able to guess at this point. But first, let's look again at how the conditions changed along our section view. As sediment was removed along and in front of the spillway, layers gradually arched up. Before cracking, the Kaibab limestone had protected the soft sediments below it. Once the Kaibab limestone cracked, the torrent dropped below the hard layer and began eroding deeper and deeper into the soft sediments below. Here it is important to remember once again that these soft sediments were still fully saturated in post-flood waters. Notice that by this point, the arching of the layers had created a downhill condition pointing backward into the mouth of the funnel. So even though on the surface, the breaching water from Grand Lake was flowing to the left, water within the tipped layers began flowing downhill in the opposite direction as directed by gravity. This subsurface flow in the layers below the Kaibab limestone explains the curiously backward barbed canyons which branch from Marble Canyon. The backward barbed canyons and sink valleys of Marble Canyon are peculiar. Drainage regions of normal rivers form surface topography in such a way that most of the time tributaries enter the main river channel at an acute angle less than 90 degrees. Here we see the Amazon. This general trait can be seen along any river. Here we see the same characteristic for the Missouri and Mississippi river systems. Most tributaries enter in the same direction as the main river is flowing, at an acute angle. Now look at the tributaries of the Colorado River along Marble Canyon. The river flows in this direction. However, unlike most drainage systems and tributaries, the many side canyons drainage enters the Colorado Plateau in the opposite direction of the river's flow, at an obtuse angle much greater than 90 degrees. In addition, these backward barbed side canyons are all basically dry now, with only intermittent flowing water. What carved them, and why do they drain backward into Marble Canyon? We'll now see hydroplate theory's simple answers to these puzzling observations. Because the layers had arched up as material was removed by the breaching of the lake, water, still in the saturated layers, flowed downhill in the opposite direction of the breaching flow above. As sediment water flowed in this downhill direction, it began eroding the still soft sediments under the Kaibab limestone. Remember, the water in these lower sediments was at very high pressure. However, the torrent of high-speed water now carving under the central crack became a flowing high-speed channel at low pressure, in keeping with the laws of fluid dynamics. Of course, high pressure always flows toward low pressure, so the water in the sediments flowing downhill also felt a lateral pull toward the central torrent flowing down the crack. These two conditions directed the flow in the sediments. As the sediment flows near the central current, the pull toward the low-pressure current became greater and greater, so that the flow hooked in and changed direction toward the central current. In this way, the backward barbed side canyons formed in Marble Canyon. They were not carved by tributary rivers or surface erosion, but by the subsurface flow of post-flood water still trapped in the unhardened sediments under the Kaibab limestone. In every backward canyon, we can see from the erosion pattern the results of the lateral flow from high to low pressure, and the hook shape of the flow as loose sediments and water spilled into the central current. Here is another photo taken late in the day. The low angle of the sun reveals the many slumped sink valleys which blanket the funnel's floor. These many slumped regions are again strong evidence that the layers under the Kaibab limestone were still soft and saturated with post-flood waters. Layers in these backward barbed side canyons are greatly deformed. Next we'll see a photo taken looking up into North Canyon, in the direction of the arrow. Notice the layers are not horizontal, but are smoothly arched steeply down toward the center of this narrow canyon. No amount of time could ever bend hardened brittle rock layers in this fashion. Some may wonder if heat and pressure could soften hard rock layers enough to cause this deformation. However, these layers are not metamorphic, strong evidence that these sediments have never seen the kind of heat and pressure required to deform them. Therefore, the only realistic explanation of this evidence is that the layers were all soft and able to deform at the same time. Of course, this flies in the face of conventional thought, but we should not be interested in protecting convention. Rather, we should be interested in explaining the evidence with physics-based mechanics. Here's a more recent view of this canyon using the Street View mode in Google Earth. So how and why did these side canyon sediments deform so dramatically? Again, hydroplate theory offers a simple yet science-based explanation. Imagine you were standing in the newly opened fracture that created Marble Canyon, looking in the direction where North Canyon was about to form. A torrent of water sweeps past you and penetrates deep into the soft layers below the crack. You observe the opposite wall of the crack forming Marble Canyon as the waters penetrate soft layers below the Kaibab limestone. Because the saturated layers are tipped up to your left, the water and sediments in the soft layers begin to flow downhill, forming many small channels within the sediments. These channels combine, forming larger and larger tributaries, as they are drawn toward the low-pressure torrent of water where you are standing. Eventually, these tributaries break through the most porous layers in the wall, spilling into the central flow of the ever-widening Marble Canyon. As this main tributary's water and sediments enter the central flow, they are immediately swept in the opposite direction by the much more powerful current that is eroding Marble Canyon. The now open subsurface tributary continues to erode the most porous layers, exposing more small channels which empty their contents into the flow. The tributary grows, forming a large, unstable flow channel that extends deep into the screen within the soft sediments. Eventually, the weight of overlying sediments cannot support this void, and the soft, uncemented, saturated layers begin to slump down as the channel collapses. No longer supported by the sediments, which are slumping below, the brittle Kaibab limestone directly under the tributary crumbles and is swept toward the central flow. The soft, wet layers quickly deform as slumping continues. Now surface water begins eroding down into the newly exposed layers from above. Hydroplate theory offers the only plausible explanation of how these narrow side canyons layers all deformed and eroded so dramatically. We will now turn attention back to the southern end of the Marble Canyon tear. The incessant flow out of the funnel continued to wash away huge sheets of Mesozoic sediments, exposing more and more of the Kaibab limestone. You probably have guessed what happened next. The western shoreline of Hopi Lake was undercut by the flow out of the funnel. The deep fracture in the Kaibab limestone further compromised Hopi Lake's floor. Now notice the elevation of the two lakes. At approximately 5,950 feet, Hopi Lake, with an estimated volume about that of Lake Huron, sat about 250 feet in elevation above Grand Lake and its dumping waters, which by now had eroded hundreds of feet down through the Mesozoic sediments. The potential energy of the waters held high in the basin of Hopi Lake was staggering. In a tremendous rush, the western edge of Hopi Lake breached even more catastrophically than Grand Lake. The concentrated erosive power in this new current quickly tore through the soft Mesozoic sediments far north and west of Hopi Lake. Let's again view how this affected the topography of our cross-section. Hopi Lake is behind us in this view. Hopi Falls rushed in here 250 feet above Grand Lake's waters and powerfully flowed far into the screen away from us. In this way, the upper sediments were rapidly washed off of the Kaibab limestone by Hopi Lake's waters. The weight of these sediments was quickly removed far northwest into the screen. This set up the conditions that produced the upwarping of the Kaibab Plateau and the massive sheet flow of the great denudation of Mesozoic sediments off of the Kaibab limestone. A small-scale yet more dramatic demonstration of the mechanisms at play in forming the Kaibab upwarp can be seen by squeezing a water balloon in your hand. The water pressure in the balloon will always equalize. When squeezed, the gaps between your fingers cause the balloon to bulge locally where it is unsupported. Think of your fingers as the sediments on the Colorado Plateau. The balloon membrane is the thick granite crust below the sediments, and the water is the pressurized liquid magma trapped under the crust. If you remove one finger, the pressure in the water immediately forces the unsupported membrane up into the gap, creating a bulged or upwarped section in the surface. This same principle of fluid mechanics was at work under the Colorado Plateau, as water from Hopi Lake quickly removed sediment from a very localized area. Naturally, this sudden imbalance of forces caused a response as previously restrained massive blocks in the crust rapidly rose and were hydraulically lifted up, seeking a new static equilibrium. In this way, the Kaibab Plateau literally warped up above its surroundings. The brittle, already fractured Kaibab limestone ripped more as it was bent by the upwarping layers. We'll soon see the dramatic results of this continued fracturing of the Kaibab limestone. Today we call it the Grand Canyon. From the surface view, the flow from Hopi Lake quickly scoured off the Mesozoic layers over a wide area. The sediments were carried to the west by the combined breaching from both lakes. However, another source of water was also at work. Remember, after the flood, all of the sediments were still fully saturated. The water within was released as massive and sudden flow from the breaching lakes eroded and flowed over the unstable, soft sediments. Soon, most of the soft sediments above the Kaibab limestone layer began to move and flow off the Colorado Plateau in a process called sheet erosion. As the Kaibab limestone was exposed by the breaching lakes, pressure far below grew and this exposed area began to rise. The brittle layer soon fractured further right across the top of the rising Kaibab Plateau. As the Kaibab continued to rise, the open fracture was quickly undercut by the breaching waters, and soon became a truly grand canyon. This explains why the Colorado River today seems to inexplicably cut through the mountainously high elevations of the Kaibab Plateau. While trying to explain the formation of the canyon via a small river cutting through a mountain is truly inexplicable, by now it should be clear that a river had nothing to do with this region's unique features. Realize that the canyon shown here in a flooded state would not yet have existed, but we'll soon see the mechanism that formed it. As the Kaibab Plateau rose, bulged, and stretched the exposed limestone in tension, the end of the Marble Canyon fracture was at the highest state of stress. So the rip naturally continued from this high stress point and followed the path of least resistance, where the limestone was under the greatest stress, due to the bending state it was in. The apex of a bent plane would be under the most tension. Rock is extremely weak in tension, so the top of the upwarp basically tore in half as it bulged up. So rather than Grand Canyon's path directly through the imposing Kaibab Plateau being a troubling puzzle, we see this catastrophic explanation aligning with expectations of cause-to-effect reasoning. As Hopi Lake catastrophically drained, subsurface flow ripped up sediment on Hopi's basin floor, and the drainage basin of the Little Colorado River formed a deep side canyon into the much larger canyon that was forming. We'll now focus on this area of the section view and discuss the forces involved with carving the Grand Canyon so deep and so wide. Initially, the region was in a state of equilibrium. However, conditions were by no means stable, as most of the sediments were still saturated with post-flood waters. I keep mentioning this because it is critical to understanding how so much material could be eroded and transported so quickly. Had these sediments been hardened rock, there would only have been a grand gorge, not a wide canyon with so many huge side canyons. As the upper 1,000 feet of sediments were washed away, we again see the imbalance of forces. Water in the remaining adjacent layers began spilling out the newly opened faces, adding to the volume of the breaching lake waters. Evidence of these eroded upper layers ringed the perimeter of the exposed Kaibab limestone. The Kaibab Plateau rose up. The limestone was stretched in tension and split. Waters from Hopi Falls high above concentrate at the fracture and rapidly undermine and erode the limestone. Once the layers under the Kaibab limestone were compromised and exposed to the massive spillage from both lakes, a truly grand canyon began to take shape. Soon, blocks of Kaibab limestone fracture and are swept into the powerful flow. The center of the Kaibab Plateau to the north, being completely unrestrained by overlying sediments, naturally began to rise more rapidly than the layers to the south. As occurred in Marble Canyon, once again, as the canyon walls quickly eroded, water within the saturated lower sediments flows from high pressure toward the low pressure central flow, which in this view is directed away from us into the screen. However, because the layers to the north were lifted higher, subsurface waters had more potential energy on the north side, and therefore flowed and eroded more powerfully toward the central flow than the south side. We can now explain the uneven erosion pattern of side canyons along the portion of the canyon that cuts through the Kaibab Plateau, and why many side canyons align with perpendicular faults. This subsurface water not only explains why side canyons eroded so deeply, but also why the northern side canyons eroded more than side canyons to the south. The side canyon's south rim is about 1,000 feet lower in elevation than the north rim, so the exposed southern walls slumped and eroded less powerfully than their northern counterparts. From above this section of the canyon that cuts through the layers of the Kaibab Plateau, the dramatic difference between the canyon's erosion patterns north and south of the river is clearly seen. Moving west and off of the raised Kaibab Plateau, The north and south rim on either side of the river are not greatly displaced in elevation, so we expect and observe that the main channel of the canyon eroded more evenly where the slower and more even sheet erosion of the Great Denudation caused material to rise at a more even rate. Let's look back at our section view and discuss in a bit more detail what cut so many long, deep side canyons and why many align with faults that are perpendicular to the river's flow. Remember, today, these long side canyons have no significant water source that could erode them. Each of their drainage basins are too small to support continuous flow of even a small river, and certainly not sufficient to sustain the type of erosion the Colorado River has allegedly produced. Yet these side canyons are cut nearly as deep as the main canyon itself. The traditionally proposed mechanism of river erosion are clearly out of sync here. Hydroplate theory again offers a grounded explanation. The source of water that cut these side canyons was the subsurface water within the sediments themselves. Remember, the top layer of the canyon is the Kaibab limestone. After this limestone had split, and the main flow out of Hopi Lake had undercut deep into the soft sediments under the Kaibab limestone, the brittle layer crumbled and fell into the powerful flow. Remember that the hydroplate theory proposes that the Colorado Plateau formed due to hydraulic lifting of continental blocks. As these deep blocks rose relative to each other, many faults formed in the plateau. Most of these run perpendicular across the Grand Canyon. As these blocks moved, vertical shear lines had developed in the soft sediments directly above the fault lines. These shear lines also ran perpendicular to the canyon in line with the faults. These shear lines became the natural weak spots in the layers where trapped water within could flow toward the lower pressure, high velocity central flow that was cutting the main canyon. As subsurface flow increased along these shear lines, more and more sediment was carried along and swept into the central westward flow. Erosion and slumping continued all along these shear lines above the faults. Of course, this erosion and slumping of the lower sediment layers caused the Kaibab limestone above to fracture and crumble along these faults. Now we've seen why the higher altitude of the Kaibab Plateau on the north rim caused more powerful erosion and therefore longer, larger side canyons than on the south rim. Sediments on the north side of the canyon were lifted 900 to 1,000 feet higher on the Kaibab Plateau than the layers south of the canyon. Therefore, water and sediment north of the canyon had more potential energy for erosion than sediment to the south. In fact, this trend continues around to the northeast face of the Kaibab Plateau. There, the erosional difference is even more pronounced. This area on the northeast side of the Kaibab Plateau is called Nankoweap Canyon. Here, the higher elevation of the Kaibab Plateau is easily seen by the trees that grow in the cooler environment on top of it. Notice how as the southern rim drops in elevation off of the Kaibab, there is even less and less erosion in the canyon. This feature again aligns with hydroplate theory's proposed mechanism for what caused the canyon's erosion, namely that the layers were not yet cemented and still fully saturated with post-flood waters. The higher the layer topography rose, the more potential energy was added to the trapped water in the soft layers, and the erosion resulting was proportional to these conditions in the layers at every point along the canyon walls. This explains why the much higher north rim of the Kaibab is deeply eroded, even along the steep backside of the East Kaibab monocline. Let's take a moment to point out that this has nothing to do with the river at all. The Colorado River has pretty much the same erosive cutting potential on either bank. So why is the erosion so different on either side? Again, we see the river cut the canyon theory fails to deliver coherent explanation. We'll now cover in detail how the Nankoweap side canyon formed here on the East Kaibab monocline. As the Grand Canyon was eroded to the southwest, the rising Kaibab Plateau steeply tilted layers as it rose and began forming the East Kaibab monocline. At some point, the water-saturated layers could no longer support their own weight on such a steep incline. The Nankoweap side canyon was soon carved by this landslide. The yellow line is the drainage basin of Nankoweap Canyon. Again, we note the erosional mismatch and wonder how a river could have produced this. Much material has eroded off the face of the Kaibab Plateau, while little has eroded from the opposite side of the Colorado River. The small creeks that only intermittently flow out of this dry canyon and empty into the Colorado River do not have the erosional power to have excavated all this material. The Kaibab limestone on the top of the Kaibab Plateau sets at around 8,100 feet in altitude, while to the east of the Colorado River, the same Kaibab limestone sets at least 2,000 feet lower. Perhaps if multiple powerful rivers spilled off the canyon from atop the Kaibab, then we might be able to explain this erosional mismatch. Of course, the Kaibab Plateau does not have enough surface area to support rivers, and there is zero evidence of rivers ever flowing into Nankoweap Canyon in this way. Only subsurface water in uncemented layers, as explained by hydroplate theory, offers an answer for the source of water for this uneven erosion. If we view a cross-section of Nankoweap Canyon, we'd see that as the block under the Kaibab Plateau rose up, water trapped in the soft sediments on the steep slope that was formed naturally flowed downhill, and a massive landslide soon slid off the Kaibab to the right and directly into and over the newly exposed tipped layers that were lifting along the fault monocline. As the loose sediments spilled out over the monocline and slowed, large boulders were deposited on top of the tipped monocline layers. As all this was happening, remember that the discharge from both Grand and Hopi Lakes continued to sweep away most of the material. At several points, the landslide carved through the tipped monocline layers, forming deep channels. This is how Nankoweap Mesa formed, and why the top of this mesa is covered with material from a landslide and rockfalls. There's simply no other mechanism to explain how landslide material could be lifted onto the top of this peculiar land formation. This also explains why the curiously small and rarely flowing Nankoweap Creek has the largest delta deposit in the Colorado River of any of the Colorado's tributaries. If the Colorado River really has the erosive power to carve through the solid rock of the entire canyon, why has it been unable to sweep away this relatively loose material of this large delta, which to this day has redirected the Colorado's flow around it? Looking more closely at this delta, it should be pointed out that dense boulder fields lie high up along the sides of the delta. Obviously, that tiny creek in the center did not lift such large boulders close to 200 feet up the sidewalls of the delta. Many boulders are larger than a man. The prominent boulders pictured here in the delta's south sidewall measure at least 10 to 15 feet across according to Google Earth. The following reference shows more photos and descriptions of these boulder fields. Once again, evidence clearly aligns with the hydroplate theory scenario of a large-scale recent landslide event. We now understand the mechanisms by which the Grand Canyon was rapidly eroded, by both subsurface water and breaching lake waters that cut deep into the sedimentary layers across the Colorado Plateau. As sheet erosion continued off the western edge of the Colorado Plateau, and more Kaibab limestone was exposed to the west, similar imbalanced forces caused continued westward propagation of the fracture, followed by more erosion, slumping, and subsurface flow along newly exposed faults carving the western regions of the canyon. The removal of so much sediment from the canyon set up the conditions that created the canyon's inner gorge. We can now explain the forces and failure mechanisms that produced the inner gorge, and understand why this deepest part of the canyon aligns with the raised Kaibab Plateau. Again, it all has to do with the balance of forces and recognizing the failure modes of materials. The deepest and extensive erosion and widening of many side canyons occurred in the midst of the newly raised Kaibab Plateau, and the weight of so much material was removed that another imbalance of forces had developed. This placed the now exposed crystalline bedrock of the continent itself in bending tension. Even crystalline rock is exceedingly weak under tensile loading, so it too fractured along the deepest region of the canyon, right under the now raised but split Kaibab Plateau. As bending loads were relieved, the fracture grew and opened up to become the 46-mile-long, narrow, steep, and jagged inner gorge of the Grand Canyon. Hydroplate theory shows these features had nothing to do with the river, and everything to do with simple applied mechanics and known failure mechanisms of the materials. As pointed out in the beginning, a river would have smoothed the walls of even the hardest rock over millions of years of cutting. Yet the walls of the inner gorge are exceedingly steep and jagged, as can be viewed by anyone while in the street mode of Google Earth. This is the view from the river at the red circle, as you enter into the inner gorge of the canyon. Looking first at the north wall, then down further into the canyon, and then to the south wall. Look one more time at the steep, jagged walls of the inner gorge and see if you still think river water cut this imposing feature of the canyon over millions of years. Now that we've seen the canyon's formation, we must ask, where did all this flowing material go? Did the river slowly carry sediment grain by grain over 6 million years? If so, remember that only explains the 800 cubic miles of the canyon's sediment and perhaps a fraction of the sediment removed from the ancient lake basins. Again, we'll see that the catastrophic explanation of hydroplate theory fits the evidence best, by showing not only where the canyon's 800 cubic miles of sediment went, but also where the 2,000 cubic miles of additional Mesozoic sediments went. Hydroplate theory even explains how an additional 600 to 800 cubic miles of sediment was scoured and removed from the floors of Grand and Hopi Lakes as well. Here we see the southwest end of the Colorado Plateau along the dashed line, the Grand Canyon, and the 10,000 square mile area around the canyon that has been scoured of Mesozoic sediments. The Colorado River empties into the Gulf of California. So, is there any evidence of a massive flow of water and sediments off the western end of the Colorado Plateau? Interestingly, above the Colorado River, all along this section from the west of the Grand Canyon to the Gulf of California, lies a high floodplain. In 2011, the United States Geological Survey completed a detailed study of the broad 400-mile-long floodplain between the western end of the Grand Canyon and the Gulf of California. The study actually concluded that the Colorado River must have recently experienced a single rapid flooding event in which almost all the sediments below the floodplain were deposited. Just south of Bullhead City, Arizona, we can see evidence of this floodplain and the strong evidence that it was a turbulent event. Here, a mile east of the Colorado River and 100 feet above it, are well-rounded boulders whose transport required sediment-rich high-velocity water. The rounding of these boulders shows that they were once tumbled in a turbulent flow. Only a large-scale event such as what we've just described could deposit such large rocks so high above the basin that now drains into the Colorado River, far below. Hydroplate theory expectations align precisely with the evidence. In the recent past, before any river existed, a massive, fast-flowing flood of water and sediments followed the low-lying topography from the Colorado Plateau to the Gulf of California. This massive flow, lasting only weeks, formed the floodplain discovered in 2011 by the U.S. Geological Survey. Some of the remnants of the deposited sediments remain today in this area around Yuma, Arizona. This explains the extraordinary amount of sand that fills the Imperial Valley just north of the Gulf of California. Every year, many flock to California's Imperial Sand Dunes, also called Algodones Dunes, in recreational vehicles. These vast sand dunes were deposited by the huge surge of water as it emptied into the Gulf of California. If hydroplate theory is correct, then a chemical and isotope analysis of these sands will show that they came from the Grand Canyon region. Finally, let's look at the Colorado River, namely its delta, as it enters into the Gulf of California. In addition, we'll investigate the northern basin of the Gulf of California and see the final destination of most of the sediment that was scoured off of the Colorado Plateau. This also builds more evidence that the Colorado River did not transport this material. River waters are slowed as they enter the ocean. This is due to the drag encountered by the larger body of water. The slowing removes the ability of the flowing river water to continue to carry its sediments, so they quickly settle out adjacent to the river as it enters into the calm and much larger body of water. In this way, a slightly raised plain forms in front of and around the exiting river, which in turn splits and branches through the plain of sediments, forming a delta. If the Colorado River had slowly deposited all of these sediments over millions of years, then we should see a fairly large, slightly raised river delta in the northern boundary of the Gulf of California. Instead, the Colorado's delta is tiny. Some claim that the Colorado's delta is large, but a quick comparison of other rivers shows otherwise. For comparison, we see some large deltas of several famous rivers all viewed from 1,000 miles altitude. And here we see how the Colorado's delta stacks up. Why have these much larger rivers that clearly have deposited much more sediment not carved equally Grand Canyons? Clearly, the Colorado River could not have slowly excavated the colossal volume of sediment off of the Grand Canyon over millions of years and not have left an equally impressive delta. So rather than a large delta in the Gulf of California, we again see evidence of a large-scale, rapid flow beneath sea level. The entire northern basin of the Gulf is buried in a thick, smooth layer of sediments covering a 15,000 square mile area with an estimated volume of at least 6,000 cubic miles. Only massive pulses of dense, sediment-filled water flowing powerfully into the Gulf would be able to rapidly carry and distribute a smooth layer of sediments that far out into the Gulf. Hydroplate theory proposes that around half of these sediments were the result of the initial sediment runoff that occurred after the flood, as water and sediment drained off the continent. Centuries later, the breaching waters and sediments spilling from Grand and Hopi Lake basins carried Mesozoic sediments as well as the Grand Canyon's sediments to the northern basin of the Gulf and quickly filled the floor to its current levels, adding an estimated 3,400 to 3,600 cubic miles of sediment. In this talk, we first questioned and then set aside the dogma that the Colorado River did all of the work over millions of years via vague descriptions of erosion. Then we considered the results of a global flood, and studying the unique conditions that only hydroplate theory links together, we have reached a more satisfying catastrophic conclusion via cause-to-effect reasoning alone. We have seen the mechanisms that produce the puzzling topographic features of the canyon and its surroundings. Hydroplate theory explains all of the topographical features in this section view that were at first perplexing. The post-flood environment left the newly formed Rocky Mountains settling down into the mantle, resulting in hydraulic lifting and block faulting of the plateau, and the subsequent lifting of two large post-flood lakes on vast layers of uncemented water-saturated sediment. Breaching of Grand Lake carved the tremendous funnel-shaped spillway through the Mesozoic sediments of Echo and Vermilion cliffs. The rapid flow over the soft upper layers caused them to flow as a sheet, and the entire plateau arched up as the weight of these layers was removed, which explains the general arching up of the canyon's layers toward the southwest. Marble Canyon was created when the Kaibab limestone layer fractured. Continued undercutting and erosion of Hopi Lake's western shore caused it to breach. The area in the path of Hopi Lake's breachway had so much weight removed so quickly that an upwarp in that area occurred, forming the severely arched layers of the Kaibab Plateau and the tipped layers of the East Kaibab monocline. As the Kaibab Plateau arched up, the limestone on its top layer split in half across the apex of the upwarp. The combined breached flow from both lakes was concentrated as it eroded soft sediments, forming the main channel of the Grand Canyon. Much subsurface flow in the soft sediments caused many deep and long side canyons to form, widening the canyon more on the north rim than the south rim, since the layers on the north rim were lifted and tipped more due to the rising Kaibab Plateau. Likewise, along the northeast side of the Kaibab Plateau, tipped, water-saturated layers could not support their weight. The resulting landslide formed Nankoweap Canyon. So much material was removed from the Grand Canyon in the midst of the Kaibab Plateau that a section of the continental rock split open, forming the steep, jagged inner gorge. This event happened so recently that weather and the Colorado River has had little time to smooth the jagged edges of exposed crystalline rock in the inner gorge. So the river did not form the canyon, but the canyon formed the river. Far from being the root cause of all this unique topography, the Colorado River is merely a natural and expected after effect of the Grand Canyon's drainage off the Colorado Plateau. Now you know the hydroplate theory's explanation for how the Grand Canyon formed. I owe many thanks to these reviewers who greatly improved the content of this presentation and its clarity. Their insight and attention to detail was priceless. Thank you for patiently struggling through my early drafts of not only this but many other hydroplate theory presentations. For more information and hundreds of references to published papers containing findings and evidence which fits hydroplate theory better than conventional evolution-based theories, visit the Center for Scientific Creation website to access the free online book at creationscience.com.